As you can see, the title is Optimization Control Parameters for a PV control system in EMTP using particle swarm optimization. Our presenter is Bikrant Poudel, who's a PhD student at the University of New Orleans. His research focus is our machines and drives, power electronics and controls. So thank you very much, Bikrant, for presenting this year's EMTP user conference. Before you start, I would like to invite all the attendees to type their questions in Zoom during the talk, and then at the end we'll do our best to answer your questions. All right, Bikrant, the floor is yours.
Thank you. So my name is Bikrant Poudel. Good morning, everyone. So I'm from University of New Orleans, and my presentation today will be about optimization of control parameters of grid-connected PV in EMTP using particle swarm optimization. So this is how my presentation will go. I'll start with the introduction, give you a test system description, which is a file available in EMTP itself. I'll talk about generic optimization process. Then I'll show you how the PSO is implemented in EMTP using JavaScript. Then I'll present to you how the optimization, like how that algorithm work and what are the results. So to start with increase in energy penetration into the power grids, this makes the integration study of PV plants to power grid and the related control strategies very important. It can not only help utilities with the optimal design and operation of PV, but it can also prevent the instability. So the portion the algorithm will work, the optimization will work will be on this instability of the system, as well as we are trying to bring the performance of PV, the real and reactive power performance, to a steady state level, to a rated level. So usually the control gain parameters that we use in the PV plants, there are lots of them, has a significant impact on PV plants response during the fault, as well as a fault recovery. So that also impacts the rest of the system. So we have to be very careful while we are trying to choose the controller gain parameters. And usually manual tuning is possible of these parameters, but if we have to consider a lot of multiple scenarios, multiple fault scenarios, or we have to include multiple PV parks or PV plants in the same system, then the manual sensitivity tuning is very time consuming. And sometimes it might not even be possible considering the number of scenario and number of simulations that we have to run. So in these cases, we can use some optimization techniques such as PSO. Since EMTP can support JavaScript, we can implement PSO in JavaScript, and that can run the simulation, do the optimization. So that's the process that we have done. So talking about the system description, we have taken the EPRI benchmark PVV1 file that's inside the example files in the EMTP. So basically it's a 6-bus system with 2 load buses here. PV is connected to bus 1, and then we have 5 transmission lines, and we'll place some contingency. We have modified a few parameters for this particular park as compared to the example, because we wanted to make it as real as possible. So there was a real plan that we considered during our research. So we have modified some parameters to match that particular plan. So the modification, the PV specification that we have is the PV is operating in Q control mode, but this is not, for the algorithm to work, you don't always have to have it on Q control mode. You can just use power factor mode, control mode, or V control mode. Anything can be implemented. For now, it's done in Q control mode. And the value of converter control voltage regulator gain KB is set to 0.5. It was, by default, it might be something else, but we set it to 0.5 after some manual tuning. The power control parameters, that's the PI control parameters, KP and KI were set to 2. So these were the modification done on the controller mask side, and the real power output was set to 45 megawatt and reactive power was set to minus 19 megawatt. And talking about the contingency, we are considering 3 contingency. During the optimization, we'll be considering contingency 2, but just as an example, we have also included contingency 1 and 3. So first contingency will be fault on bus 1. It's 6 cycle 3 phase to ground fault on bus 1. So that's our first contingency consideration. Second one will be the same contingency, but we'll also take the bus with the line between bus 1 to 2 out. So it's kind of extreme kind of contingency that we are considering. Another will be we place a fault at bus 1, and then we take the line between bus 3 and 2 out. So those are the 3 contingency listed. So now with these parameters that we ran a simulation for contingency 1, where the fault was simply placed at bus 1, we could see that right after the 6 cycle fault, the PV system can actually stabilize within a second. But if you see for the contingency 2, there are a lot of oscillation and it keeps on going. So here the problem is the PV could stabilize for that set of control parameters for this contingency 1, but it could not settle for contingency 2. So from here, what we can say is for same set of control parameters, the response might be different for different contingency. That's what we saw. And for this, controller gain parameters have a significant role on how the PV will respond during the fault recovery, and as well as interaction with the rest of the system, because it created some voltage oscillations there. So the control parameter of PV can be manually tuned. Before this research project, we are actually doing some sensitivity to manually tune some parameters, but it was very time consuming. Even with one fault and one PV plant, just to make sure everything works, we had to do 20 or 30 simulation. But if you consider multiple fault scenario so that your PV will work each and every time, so that's a lot of simulations. So that's why manual tuning is complicated. We don't want to do that. Or if there is another process that's better, not so time consuming, we want to follow that path. That's why we are trying to do a systematic optimization algorithm to tune those values. And up to this point, for this particular presentation, I'll only be considering these 3 variables. That's converter control KV, power control KV, and KI. But it's up to you on your implementation. If you want to add more, if you want to add some settling time, if you want to add some other parameters, then it's a very simple modification to the code itself. So saying that, now let me go on and start talking about optimization. So for our optimization, there are a few basic assumptions that we took. The main thing is we are considering our PV plant as a black box model. In EMTP, you can go inside the model, you can see all the control implementation, which is very nice. But what we think is if there is some proprietary information, the manufacturer will usually not provide you with the model that you can go inside and change change the control system itself. What you might be able to do is you might be able to access the mask of that system and access the parameters, control parameters. So that's the initial assumption that we took. And even without the access of the internal control system, this kind of optimization will work. We'll simply consider that PV plant as a black box model. That's why the algorithm we have chosen is a heuristic kind of algorithm. So now talking about the optimization process itself, usually the optimization process searches for the best set among the set of available parameters or set of available solution set. It can either be defined as a minimization problem or maximization problem. In our case, we are defining it as a minimization problem where we want to minimize our objective function. So here you can see that the equation 1 is a generic form of the minimization problem where we're minimizing a function f of x subjected to a certain constraint. So now our function f of x will have multiple objective, meaning we want to do 3 different things here. So all of those 3 different objectives, which I'll discuss later on, will be our objective function. And then the constraint that we are talking about here will be the range of all those variables. Sometimes we know that the value of the converter control can not go below 0 or it cannot be negative. So we can actually place that constant during our optimization. Or if we know a good range of values, we can only search within those values. So there's some constant that we can use so that the optimization run faster. We don't have to search a huge range, but you can always increase these constant or not even put a constant and do optimization. So that's also possible. So talking about the PS, so first thing we have to know is it's kind of heuristic optimization. By heuristic, it means it's based on trial and error. It does not require an exact equation. We don't have to have the overall equation of a system to run this kind of optimization. Heuristics are usually adopted if the system is too complex, and it's adopted to find an acceptable solution within a sensible amount of time. So instead of searching entire domain or doing some sort of brute force optimization, searching each and every point, what we can do is we can run this random algorithm. It starts with a random value. It has some process where it will search some neighborhood, some other region to find a solution. So the aim with the heuristic optimization usually is to find a good solution that is optimal or very optimal. Most of the time, it will find a very optimal solution. But if you don't want to run that optimization for too long, it will still take you to a very good solution that will work for your system. So PSO that we are implementing, which is particle swarm optimization, is also heuristic optimization. So it's based on trial and error, or it starts randomly. The value, while we initialize a value, we do it at random. So it's based on swarm intelligence technology. So usually it tries to mimic how the birds will fly or the schools of face will flock. So in this, if you see whenever birds fly, they try to make a particular formation for flying so that it's efficient for them. Even fish does that. Whenever they swim, they have a certain formation. Most of the time it's for their security. Sometimes it's for their efficiency on flying or swimming. So these kind of act is actually mimicked here. So it's a population based heuristic algorithm. Population based meaning if we are selecting 3 parameters, it will first start with 10 sets of those 3 parameters. So 10 different sets of KP, KI, and KV. So that's our population set. Each set of KP, KI, and KV is called a population. And most of the time, even in the literature, PSO is adopted in electric power system for many times. The reason for that is if you only have to deal with few parameters, it's very fast. But now if you have a lot of PV plants with a lot of parameters, you can still use GA. You can still use other algorithms, genetic algorithm or other algorithm, which are still heuristic. But in our case, we tried first started trying GA, and we also tried PSO, and PSO worked quite well and it was faster. So we went with this. But as I said, if there are other things that you want to try, a lot of other scenarios or a lot of other PV plants, you can still go with other algorithms. So in this particular application, the problem of dimension depends on the number of parameters. Usually with optimization, if there are a lot of parameters to optimize, then the problem dimension is higher. Right now, our dimension is 3 because we are only selecting just 3 parameters. But if there are more, then problem dimension will be significantly higher. If you want to optimize maybe 10 parameters, it will take some time because that's very huge problem dimension. So the time it takes to optimize something also depends on the problem dimension. And in PSO itself, a function is minimized over objective function. I'll talk about objective function in next slide. But it always starts with an initial randomly generated population points. So I already talked about that. So we start with 10 sets of KP, KI, and KV, and then we run simulation and go from there. So associated with each population set or each of those particles, KP, KI, and KV are 3 particles. They have a velocity vector associated with them. That means first we'll try running optimization at a point with a certain value of KP, KI, and KV. And after that, we'll move those points somewhere and see how it will perform. And at each point, we'll calculate the value of our objective function, which will give us the cost, meaning how well that algorithm is working. So we'll do that, and based on these things, based on the performance, based on the previous velocity or next velocity, it will create entire new sets of new population with their new velocity. And this process goes on and on until we get to an optimal point. So it's simply like birds are flying in the sky. Currently, they're at a certain place. They did not get any food, so they move their position with a certain speed. They move from one place to another place, and there they will find some food. They will do this until and unless they get some food to eat. Right? Same thing happens here. Our algorithm, KPK and KV, those 3 particles are similar to birds. They will start moving here and there until they get to a point where it's optimal, where the cost is low for us. And what those points do is they keep track of their best so far position, because while roaming around, they might not always go to a good place. Sometimes the cost will be too high. So they always keep track of their best so far position so that they can go back to there. And this particular point is called personal best or P best. And what the algorithm does, it also tracks the overall best of our position, which will be called G-base. So that's the global best. And this is PSO algorithm. This is simply, I'm putting in algorithm form what I explained before. So we generate initial random population or positions for KPK and KV, have some velocity associated with them. Then we'll do the simulation. From EMTP, we'll get something back. Based on that, we'll change the position as well as velocity. And we keep on doing this until we have a stopping criteria which is fulfilled. So stopping criteria, usually with PSO, you can set it as a number of iteration. We usually do 100 iteration. Or what you can also do is, if you know that your cost will never be less than 1, you can set that as stopping criteria. So if you reached a cost of 1 or 3, you can stop your algorithm. For us, I have set the algorithm to stop when the cost is 3, so you'll see that. So now, talking about PSO implementation on the PV system in EMTP itself, the objective functions that we have is, first is to reduce the post-fault oscillation, what you saw before. So to reduce that instability in the system. So we want to reduce that time make that time as minimal as possible. And some of the time, the real power right after the fault is spiked to a negative value. And it happened a lot for our test system. So we also thought of removing that, and it was possible by modifying the parameters. So that will also be considered. And we also want to maintain the reactive power to the desired level or rated value. So what happens is, if the parameters KPK or KV are too low, it takes a very long time for that plant to settle. We don't want to wait maybe 10 or 15 seconds for plant to settle. So we make sure that right after 5 seconds or 4 seconds, that's the time interval you can choose. Within that time, your PV park is stabilized with the value that you use. It can be 2 seconds also. So that will be monitored. And if that does not happen, there will be some, will penalize the algorithm for not doing that, so that another value will be selected. So to calculate these things, what we have done is, we'll measure the reactive power after some time. We know that it should be stable within a second or two. So after a second or two, we'll check for that reactive power. And if it's not very close to the rated value, then we'll raise a flag. Flag means a block diagram will simply output 1. So there's a block diagram to detect this. It's a simple comparator implementation in EMTP. So that will just change its value to 1. Similarly, we'll monitor the real power. If there is a very high negative power spike, that will also be flagged. So that will be flag P. And after that, for the oscillation, right after the fault, at interval of 0.5 seconds each, we'll monitor oscillations. And if there is oscillation, then on that particular time frame, then we'll raise a flag for that particular time frame. So after getting a flag, also let me explain like how we do it for the oscillations. It's slightly different from other two. For real and reactive power, it's easy block diagram implementation. For the oscillation detection, it's usually we are implementing RMS energy filter. So it's oscillation detection. It simply takes inputs, uses some bandpass filter, squares it, then it averages the value out and get a square root of that. And after this, even if you get some value, that means there is an oscillation. So from all these flags, we get the value. We get to know if there is some oscillation or not. And from those flags, we calculate our cost, which is also called fitness. So if you see right here, if the reactive power was not stable, then it has a very huge consequence. So the number of bits that we might be monitor might be 18. So if that's the case, then if there is a Q flag, that means if the reactive power was not stable enough for us, then it will get multiplied with 2 raised to power 17, which will give us a very huge value. That will penalize our algorithm very hard. Same thing with the real power. And if you see at this point right here, that means for first 0.5 seconds, there was some oscillation. So it has a very minimal effect on the fitness itself. So based on how long those oscillations are, or if their reactive power, if the reactive power was stable or not, or real power was negative or not, this fitness will be calculated. And with that, with the fitness that's calculated, our algorithm can go on. So this is sometimes I'll refer to it as fitness or sometimes cost, but that's our objective function. And this is how we are calculating objective function. And due to this implementation, we actually don't need to know how the control system are within the PV plant itself. So this is basically monitoring the block diagram on EMTP while the simulation is running, sending those values that the block diagrams are giving us back to JavaScript using mplot. We have to use mplot in this implementation, and from there calculating the fitness. So this is how everything is running. The actual algorithm will run. So we have a PSO implementation in JavaScript done. I'll show you snippets of code later on. So what it does, it randomly initializes everything. It gets a value of control parameters and save it onto the file. So simulation file is side by side. So it will save it to that simulation file and then run the simulation from the script itself. And after while running the simulation, P and Q will be monitored for oscillation, negative real power, or reactive power. So these flags will be raised or not raised, which will be sent back. So at this point here, what's happening here is we're implementing our mplot block on EMTP. That mplot block will simply save the value of all these flags to a result file, and PSO actually gets those files back and parses that file to see what are the values, and simply from those values it will calculate the fitness function. I'll also show you the code for that, and based on that fitness function the PSO implementation will change some parameters again, and this will keep on happening again and again until we reach a certain stopping criteria. Saying that, let me show you the implementation in JavaScript. The first thing is initialization. I'll be zooming into these slides and showing you that. So it's basically even this file. We started with the example script file in EMTP, and from there we did all the modification. So here you have to have object creator script parsed, open and save parsed, as well as since we are trying to modify the parameters of PV Park, we also need to parse the script file for PV Park, which is available in EMTP itself. So even if you just write these lines, it will parse those for you. The next thing to do is we have to save the current circuit in some variable so that we can access it later on. So current circuit, which is open, which is our simulation file, will be saved to a variable called circuit. And from there, after that, we are parsing the standard function. So inside in standard function, what we have is we have things which will with which that mplot will save results to a result file, and it will also read that file back and parse that file. Or if we need to save some value during the optimization run, then we'll use the standard function. All the functions we have written is inside there. That will save some value inside some files so that we can monitor how the algorithm is running. After that, we have to initialize some parameters for PSO. So basically here you can define if you want to start with 10 population set or 20 population set, you can write it right here. And you can also define the number of simulations. So if the number of simulation is 10 and we are using 10 sets of KPK and KV to start with, the total number of iteration it will happen is 100. So if you change these, it will change the total number of iterations or total number of simulations that you run. And similarly now for the PSO itself, we have some parameters that we need to initialize. So we have initialized it right here. All of these parameters belong to where you calculate the velocity and calculate the new point. So it was explained in the algorithm itself. So those are initialized here. And after that, if you want to put some constraint on the variables, you can do it right here. Right now, I'm only doing it for maybe 1 or 2. But I have 3 variables. I did not want to include a very tiny picture with a lot of details. So I'm removing some of the redundant thing that I have done. So basically, if you do it for KP, similar way, you can do it for KP or KI, anything can be done. So these are the limits for the variables. So those are the constraint that I was talking about. Let me go back. Now, similarly, second step is initialization of the population in random. So here, if we have 10 population, we have to initialize them in random, but we have to be within that constraint. So this part of the code actually does that. We'll simply initialize 10 sets of KPK and KV at random. We're using a random number generator here. Then we'll save those to the variables which we'll use later on. After that, most of the time, once you run the simulation, and if there are like 100 simulations that we have, what happens is you cannot do anything on the EMTP side. Once it runs, it runs. So you have to leave it, and you don't know what's happening for the system. So best thing to do will be to save the intermediate data to a text file so that we can open it with some apps like Notepad and monitor it. So that's being done here. So There, we just initialize that file and make it ready so that we can save the value KP, KI, and KV, and also the cost at each run. And after any iteration is finished, after we get the cost, we also use this function called print set, which is inside the standard function, to save those values. So we'll do that. Okay, now the actual thing will be to run PSO itself. While running PSO, let me zoom into this section of the code. So, okay. So in this section, what we do is, I'm sorry, I think I'm on the wrong slide. Let me just go back to running PSO, this one. Let me just try to zoom into the section that I need. Here this way. Yes. So here you can see that while running the PSO, we have two loops. One is for like all the inner loop is for population, and outer loop will be for the number of iterations that we want to run. So basically, if we have 10 population, the inner loop will run 10 times, then it will happen for 10 times for the outer loop. So in total, it will be for 100 times. So we start with the variables. Variables for each set of KPK and KV will save that to a PV park. This is how you save those values to the PV park. We know the variable assigned to them, so we'll use that, we'll save that, and then we'll run the simulation right here. In this one, I'm just simply running the simulation, but you can also add another similar section where you'll run the load flow. Here, the load flow value will be 1, time domain will be 0, and if you do the same code again, it will run the load flow for you. And this one, we're just running the simulation. And then after that, we find the cost. We are using set mplot params 2 functions to do that. I'll explain about that function later on. But this function will give us the cost for that particular run. And we'll, based on that cost, we'll find out the personal based as well as global based, change those values. And after that, we'll change the velocity for each of the particle. Right now, we have 3 variables, but I'm only showing 1 because it's redundant. You do the same thing for other variables too. So for KV, this is how you change the value. The value W, C1, C2 are based on the, whatever we initialized before in the initialization section. You can also change the value of W, C1, and C2. Most of the time, the PSO algorithms are very problem specific. So the value that I chose work very well for this particular simulation might not work well for other simulations. So usually we have to adjust the value of W, C1, or C2. Those are the velocity constant that you might have to change. So we set limit, and then after that, after everything is run, again, we'll run the simulation again and again for other values. So that's how it will work. So that was for the PSO. After PSO, since I was talking about the matplot parameters, let's see if I can. Okay, so this is how that saving the value from EMTP to JavaScript works. So first, what we do is we have to have an mplot block on MATLAB where you have to initialize the output file to be. You can for this one I have done result.txt, so have that on mplot. So it will run the file. Then from the it will run the simulation. So the simulation will be run by the JavaScript. And for all the outputs that we get, each of these lines corresponds to a particular output of a particular block, which are flags for us. So those will be saved to a file called result.txt. And after saving those files, here we are just using mplot to save those values to a file. And after we do that, let me go to the next slide. Okay, so after that is saved from EMTP to a file, then we use Parse script. So this Parse script simply reads that file. From that file, it calculates that cost for us. That cost will be used. So basically, we have to do it in 2 steps. Usually, it's not directly. We are not directly able to send everything back from EMTP to the JavaScript. So we'll use mplot for that to bridge that gap. So mplot will read all the values of the flag, and it will save the values to a file, and which will be read by PSO. in the JavaScript side. So this is the implementation that's done right now. If there is some other method, then that might be possible. For that, we might have to discuss it with EMTP and get some help from them. But this is the current approach that we took to set the value. So after that, I don't need to zoom anymore. So let me just start the presentation now like this. So this is how our algorithm work. So here what happened was we started with some value of KP and KI and KV right here. Okay, so from that particular point had a very high cost. So if the dots are yellow or that color range, it's a very high cost. If it's blue, somewhere around here it's blue, so it means a very low cost. So we can see that the algorithm bouncing from places to places with different value of KP, K, and KV until we get to some minimal point where the cost was too low. This is how the PS will work. And to show that in the value, this is how for different control parameters, different cost, we achieve different cost. And we can see that right somewhere around here for the KP, KV, KP, and KI of 0.44, 2.42, and 2.08, we got a cost of 3. That means there was real and reactive power were on the range of what we wanted, and then the oscillation did not last too long. So that was selected as optimal point by the algorithm. So that's the best set of KP, KI, or KV that we got. And from there, this is the comparison result. So before it looks something like this, but now by using these values for the same contingency, this is what we got. So this is the optimized result in our case, and that's for contingency 2, where the system was unstable. So even after that, within like 2 seconds, the control parameters would actually stabilize the system. So that's the first thing. But now to think, will that work for others too? Other fault or other contingency too? So since that was very extreme case of fault, and we are hoping that if you do this algorithm on some certain very extreme contingency cases, that set of control parameters will work for other normal faults or other less severe faults. So this is what we got. So using those values for contingency 1, this is how the PV park will behave. Right after fault, it could stabilize easily. So this is contingency 1, meaning just 6-cycle fault at bus 1. And this is contingency 3, where we had a 6-cycle fault at bus 1, but we also remove another transmission line. So it could also work on this. So now from the results, what we can conclude is we can use optimization, heuristic optimization to optimize the control parameters. It does not need to be the 3 that I just showed you. It can be anything. And not only can we consider single fault scenario. Right now, what I'm considering is one contingency. I'm not including multiple contingency during the optimization. But in our work, what we are doing is we are actually working on a very big system. We are selecting multiple contingency point, multiple weaker point on the system, and based on those multiple weaker point, we'll do the optimization so that we are sure that the value that we choose can actually work for all the contingency scenarios. And not only you can just use one plant, you can also optimize multiple plant. In the case of PS, we have done up to 3 plants. So it can be expanded to any limit. And there we can also, if that PSO is not enough for that particular application, based on our problem domain, problem application, we can also use something like genetic algorithm. So if you want to know about further details on the application that we use, we recently we presented a paper on IEEE 2021 IEEE Kansas Power and Energy Conference. So this is also related to a similar topic. And this is the reference for that paper. So these are the references that I had on the slide. And after that, first and foremost, I'd like to thank EMTP for providing us with the EMTP software, and also they always offer advice. Their technical team is very helpful, so that helps a lot. So we are very thankful for that. So after that, if there is any question, I'll be very happy to answer those.
Thank you, Bikrant, for a very interesting presentation. So there are a few questions. One of them is, how have you been able to identify that KP, KI, and KV seem to be the most important gains to play with? And is there a general approach to help us identify what are the most critical gains in general?
Yes, so during the start of this project, it was 2 years back. So in the literature, the most common gains that were creating some sort of problem for PV was either PLL gain or the PI controller gain. And with that knowledge, we did some sensitivity. At first, we actually did manual tuning before PSO. And while doing the sensitivity, we found that these 3 parameters actually were changing the response a lot. So first it was manual tuning, manual sensitivity analysis, and from there we chose this value. So other parameters might also be might also have a significant impact. So what we can do now, we have that process, we use that process. What we do is we can actually run sensitivity using the JavaScript itself. Since we are already using JavaScript now, we don't do anything manually. We run JavaScript, we test a range of a parameter. We take one parameter, we test a range of it and see what's the cost for that particular parameter. So this same approach, even without using some optimization, we can run it to do the sensitivity. And from that sensitivity, we'll know what kind of parameters will play a big role for that particular PV park. So that's how we do this while we do the research.
So in short, once you have your model wired up with the script, it's easy to test out different parameters and see their impact.
Yeah, and if you don't want to run optimization, then it's simply about doing some basic sensitivity, which is even easier than running this optimization itself.
Right. There is one question which may be answered by the slide that you're showing right now about the values of those 3 gains before and after the optimization process.
Before it was, what we set was around 0.5 and 2 and 2 per kp and ki.
Okay.
And after the optimizer, I'm sorry, I have to scroll some here. After we got this. So for kp, even a minor change has a big effect. So if you see, usually the kp will, from the range we have tested, we could only go from 0.25 to 0.5 for our system. So that's a pretty small range. So within that range too, it has a huge impact. So we were using 0.5 right now. The optimized value is 0.44. And even for kp, it's very close to 2. So even for kp, the range that works for us usually is within 2 to 5. So usually within that range, it will try to find the values. And not only that, between these 2 values, this particular arrangement worked. But even with the value of 2.442, but the value of ki is around 10, it might not work. So even if these 2 values are the same and if it's different, it might not work. So while optimizing, in sensitivity, you'll only change one parameter at a time and see what happens. But in optimization, it will actually change all 3 parameters at the same time, so that we know this set of value will work, not just one value from that set, but all 3 while working together, they will work to make our system stable.
Right. Can you also comment on the benefits this optimization for this specific type of fault has brought in general for other? I mean, you have touched upon it a little bit, but can you tell us a little bit more? Yes. Have you done some testing with for other contingencies, for other types of faults? Is this does this seem to be optimal design for in general as well?
Yep. So right now I'm using a file, but the actual research system is bigger than this, and we do have multiple weaker points in the system. So even with the PSO, and what we are testing is we are also testing 2 plants on the same point of interconnection. So there are 2 points. So that means the number of variables will be very high for 2 different plants. And while optimizing, we are also considering 3 different contingency or 4 different contingency scenario. So this PSO will actually first run, and it will, for those 2 PV parameters that we have, it will set some value. It will first run first contingency, see how it behaves. Then after that, it will run second contingency, see how it behaves, and same thing with the third one. And now considering all 3 contingency, considering all three flags that will raise on all those three contingency, then only it will calculate a cost, so that whatever value we get will work for all those three contingency. And most of the time, what we have seen is, if we consider multiple fault scenario or multiple contingency and done optimization, the value that will that we get from that particular optimization will work in any contingency actually. So it's just about figuring out some critical point in the system. Considering those critical points, we run optimization, and after that, the value that we get from the considering those three contingency will work for any kind of contingency in the system. And it worked quite well. PSO works quite well for that. So we have done it for three or four contingency, up to 2 or 3 PV plant at the same time in the system.
And the cases that you're analyzing are usually a relatively weak grid.
Yeah.
Cases. What was the, do you remember what was the short circuit ratio for this case?
I'm not particularly sure about this one, but usually we try to get it to around 2 or 3.
2 or 3.
Yeah. So usually with lower SCR, it's highly likely that the PV will oscillate. The similar behavior that I showed you is very high, likely with the lower SCR. So above 10, we don't have to worry. Even above 5, there will no such problem. It took some time to recover, but it recovered. But around 2 or 3, you have to do some optimization so that you get a good recovery time. If not, the system will be unstable. Can you hear me? So I think I saw another question here. So I'm not sure if I'm being heard, but let me try to answer it. So how sensitive are KPK and KB to induction motor characteristic? So even for this, we have to manually place an induction motor near to the PV park and try it, which we have not done till now.
Hi, Bikrant. I believe Mihailo got disconnected. This is Henry speaking here.
Oh, yeah.
So yes, we can hear you.
Okay, sure. Thank you. So yeah, talking about the induction motor characteristic, there will be some sensitivity, because usually induction motor, if there is unbalanced fault, it will try to draw some negative sequence current. That means PV will have, if it's nearby, PV will have to supply that negative sequence current. And that's directly when the PV is trying to recover, it's during the fault right through. So basically, I believe it will have some impact, but how much we do have to test it, we haven't tested it till now.
All right, sounds good. Thank you. Okay, so let me try to get in touch with Mihailo. You can come back. In any way, thank you very much, Bikrant, for the presentation.
Sure, thank you. Do you want me to stop sharing the screen?
Yes, you can go ahead. I'm going to, oh, yeah, good thing Mihailo is back.
Yes, I don't know what happened. Sorry about that.
Yeah, no problem. Regarding questions, I believe, did we have any other questions, Mihailo? I tried to take over after you, but I wasn't sure where we're at.
Thank you very much. No, I think that was pretty much it. Actually, I had one question, and I think many of our users would like to hear this, Bikrant. It is, when do you think you could have perhaps a simplified, a generic version of your script available for us? I know we talked about it perhaps after your paper is published, but I think it would be very useful if at least a reduced, simplified version of your optimization script is something that we could share with the rest of the EMTP users.
I would say soon, because I'm actually working on it. So right now, if you see this script, I have not explained everything in detail, commented everything, but I'm actually doing that. I'm trying to make it more modular so that the functions can be interchanged. So I'd say pretty soon, I'll be able to provide you with that.
Sounds good. Well, thank you very much, and once again, sorry for my internet issue. Thank you for your great presentation, and we really look forward to having that script available to the rest of the EMTP community. I think it's a very valuable work. We're in touch all the time with utilities, with system operators who are facing weak grid issues, and this really seems like a very, very relevant work, the research that you're doing. So thank you for that.